you've got a reaction here between, that's acetic acid, right, and lithium hydroxide. Okay, so you got that double replacement reaction happening, or neutralization, however you want to view it. O2H. And you react it with lithium hydroxide, okay, and it is going and forming what? Yes, sir? Lithium acetate and H2O together. All right, they want to show you, they're asking, okay, well, what salt forms, and is it, right, acidic, basic, or neutral? So they're asking you, okay, well, take a look at the salt that forms there. So what will the resulting solution be? So which one of the ions that do we want to draw, right? We got lithium plus as one of our options, right? Or we're going to draw a reaction for the acetate ion, right? Those are our two options to draw or to write reactions for to decide whether it's basic or acidic. So is lithium. Do we want to draw that one? No, because it's in group 1, right? It would form a group 1 hydroxide, and we know group 1 hydroxides are strong. Okay, so that's no good. Bless you. Okay, the acetate ion, though, if we put that in the water, right, you're going to form acetic acid and OH minus, right? So is the solution neutral, acidic, or basic, right? Because you make OHs in solution from that particular weak base, right? The acetate ion is a weak base. It forms a weak acid, and we get OHs floating around in solution. So that solution would be acidic. Okay, the mixture or basic between acetic acid and lithium hydroxide would be slightly basic. All right, great. So today, what we're going to do, so some of you guys, well, actually, before we get into that, some of you guys on the quiz wrote out the one reaction, which is good, like the first reaction. So you got some points for doing that, but then just took a stab at it, said neutral or whatever. A lot of people on the quiz, for some reason or another, wrote out NaCl as the product and forgot that it was that you would form NaOCl. So a lot of people like omitted the O, the oxygen in there, and it caused you to think it was neutral. And that's, yeah, that was problematic sort of thing. Is that what you did? Okay. So, in any event, let's move on to buffers today. Okay, buffers kind of deal with weak acids and bases and stuff. Okay, a buffer, what do you guys, it's not in terms of chemistry, when you guys think about a buffer, what is a buffer? Okay, good. Absolutely. That's what a buffer does. Yeah, prevent. How do you usually describe a buffer? It's like the buffer zone, right? Okay. Yeah, something like that, or you know, as you walk into a high school dance, they should hand you and your date a balloon. So you'd have to get that far apart from each other. That would be a good buffer zone. Okay. Well, they'd pop and it'd be problematic, and I would just no. I chaperoned one dance, and that was enough.
Did you go to dances in high school at all?
Oh, of course I did. Yeah. Yeah. That's funny. Yeah. So, but yeah, you know, that's just an awkward place. It's an awkward place. So I'll avoid the whole dance floor situation that happens. So just let that go. All right. Okay, in any event, a buffer when it comes to chemistry, okay, is going to resist or it won't change pH. That's what a buffer is. A buffer will resist changes in pH. So it's preventing the change in pH. So just like you would think a buffer zone, a buffer would work in real life, a buffer for chemistry is something that is going to resist changes in pH. Okay? Now the way it does that is it has a weak acid or base and the conjugate in solution together. So if I were to draw that out, right, like we have HA is my weak acid, and it's in water, right? You have both, well, actually, I won't draw it with water. I'll just draw the dissociation of it. Right, I'm just going to get rid of that part. Just put it over here, ignore it. Okay, HA, right, dissociates with H to form H plus and A minus, right? So you've got our weak acid and the conjugate base. Okay. Both are present in solution, so you can make both of those and have them, a particular amount of those in each solution, okay? So you have both of those things present. So if you were to add a base, well, it would react with some of the HA and get neutralized. And if you were to add an acid, it would react with the conjugate base and get neutralized. Okay, this is how your blood works. Your blood has conjugate acid and base pairs in it to maintain a pH right around 6.8. Okay, so even if you get a lot of carbon dioxide in your blood system, and that causes it to become more alkaline or whatever, you can neutralize that to some extent. Right? It can buffer your blood to maintain your blood pH. Okay? But buffer can be broken. There's only so much of the weak acid and the conjugate base in solution to neutralize the acid or base that you're adding to it. Okay? And once you break the buffer, it's over. Okay? If I add enough base to that solution, I'll neutralize it all with the weak acid, and it will resist some pH change, and then all of a sudden, once there's no more acid left, and I'm adding in base, the pH change will be very drastic. Okay? So when we do these titration curves and stuff, you're going to see what happens. We're going to be adding base, and we're going to be neutralizing it, and the pH will change slightly. Okay? But then until all the buffer is finally broken, until it's broken, there's no more there to neutralize, you can break it. Okay? Because pretty much we talk about, Ms. Mars and I kind of talk about the acid or base that is being added to the solution as a invader, attacking the buffer, try and bust it up. And the buffer can only take so much before it breaks. Okay? So it actually resists changes in pH, unlike France in a war, right? Okay? A buffer is not like France, okay? Buffer's more like England, okay? France always surrenders pretty much right away, too. It doesn't take long. So, but, that's neither here nor there. So, all right, amen. So, looking ahead here, the deal is you've got to have the weak acid and its conjugate base in there, or a weak base and its conjugate acid. You've got to have both present to have the buffer. All right, you can't have one or the other, then it's broken. You got to have both. So if we look at these mixtures here in the first question, let's identify if we have some buffers. Okay. Okay, well, we got a weak acid here, and it's conjugate, right? So check mark that as a buffer. Both of those are in there, that's a buffer. What about this one? This is still a weak acid or base, and that's its conjugate. Okay, so that's okay, that works. It's a buffer well. Okay. Actually the buffer that's in your blood. Okay. Now this one down here. Ooh, I see some good people looking at it like, ooh, I don't know about that one. What makes you balk at this one? It's a strong, right? This is strong acid. That means, does the nitrate act as a base? No, it's not a good conjugate. Okay, so this is a no. Okay, this guy's strong. Okay, it's only weak acids and base pairs. Okay, it's only weak acids and base pairs. You can't have buffers with strong acids or strong bases. Okay, you just can't have that because the conjugate is so weak. All right. Okay, so let's go ahead and put the page here. This is probably one of my favorite equations in all of chemistry right here. This is my guy. Okay, well, my guys. This is the Henderson-Hasselbalch equation. Okay, it's fantastic. It's fantastic. It's glorious. It's on the back of your yellow periodic table now, which is awesome. Okay, it used to not be there, but it is now. All right, it's great. So easy to calculate pH with this. Okay, when it comes to buffers, and when we're doing like weak, strong titrations, Hasselbalch it up, good to go. Okay, glorious, glorious. Right. So if we look at this guy, what we need to do, we want to calculate the solution. All right, calculate the pH of the solution. Here's a typo here. It should not be 0.5 liters. For this one, it should be 0.050 liters. Okay, because we're going to take 25 milliliters of 0.5 molar formic acid, okay, and 25 milliliters of 0.7 molar sodium formate, right? Which is basically, right, formate is the anion, right, to the formic acid. So we've got both parts present. We got the weak acid, formic acid, and its conjugate base, the formate ions floating around in solution. Okay. The Ka for formic acid is 1.8 times 10 to the minus 4. Okay, will the pH change if I add 100 mils of water to this solution? All right, well, let's calculate pH of the original solution, right? So we got to do before. Let's do the before. And in order to calculate pH, we're going to use our Henderson-Hasselbalch equation. Concentration of A minus divided by concentration of HA. Now, we got to figure out what the concentration of each one of these is, right? Because we have two solutions and we're taking the 25 milliliters of each and pouring them together. Okay, so we got to find the new concentrations of our acid and our base. Okay, so let's do that real quick. So of the formic acid, so formic acid, so this is our HA, right? This is our acid, right? That guy is 0.025 liters times 0.50 moles for every 1 liter. So we've got no battery calculator. 125. 0.5 moles of our HA there. And we got to find the new concentration, right? So I'm going to divide that by our new volume, which is 0.05 liters. Right. And what do we get there? 0.25 molar, right? Okay, we could have kind of gotten there a little bit quicker, right? Because what did we do? We doubled the volume of the solution, so the concentration is going to go in half, right? All right. So I'm going to plug those in, right? Because 0.7 molar one will go to what? 0.35 molar, because we doubled the volume of the solution, so the concentration is cut in half. Does everybody understand how that works? M1V1 equals M2V2. We could do that too. All right. I just kind of went the long way there on you. We're okay with that? All right, so so we've got that figured out. The log of our A minus is going to be 0.35 molar over our 0.35 molar HA. Now pKa. Do you guys remember pKa from that one homework question? Okay. It was asking about relative strengths of acids, and it gave you all the pKa values. Right. Well, the pKa is just minus the log of the Ka value. All right. So when we plug this in, it's just minus the log of 1.8 times 10 to the minus 4. Just like you're calculating pH, you're taking the minus the log of that concentration of H+. Okay, so this is just pKa is just minus the log of the Ka value. And that's going to give it pH. I don't know why I put my calculator away. So when we plug it in, let's just double check here. Okay, great. So I do get pH equal to 3.89. There, so we're good. That works. Okay, check. All good. All right, so what they want to know is, hey, we're going to throw in 100 more milliliters of water. Is that going to change anything? Not really, right? What does it change? Right. So afterwards, change the concentration of A minus and HA, right? They're not reacting at all. We're just changing the concentration of them with the water. But what are you doing to the solution, right? The new volume would be what? (150 milliliters), yep. So 0.15 liters. Okay. What's the important part here that really doesn't change? K stays the same still. K still stays the same. But in terms of our working parts, yeah, right? The concentration changes, but what really is going to stay the same? The ratio, the ratio between the two is going to stay the same. Because we just diluted the solution with 100 more milliliters of water, right? I mean, we could calculate the new concentrations, okay? And you'd have 0.0125 moles of our formic acid, and now we just divide by our new volume is 0.15 liters. So we're going to have our concentration of HA is going to be 0.083 molar. And the other one is going to be 0.117 molar. Because we pretty much diluted by 2/3, right? So, could have done that one, M1V1 equals M2V2 as well, right? So the pH is equal to minus log 1.8 times 10 to the minus 4 between that guy, but it's the same ratio. All right, so this one is still going to be, pH is still going to be 3.89. Okay. All right, just recognize that no matter what, the volume of the solution is, okay, that ultimately the pH is going to be determined by the ratio of the buffer to itself, okay? Because that's really the part that's going to be changing. Now, if we have equal proportions, this is kind of an interesting part that will help us out later. If we have equal proportions of our conjugate and our acid, what does this turn into? Like if this is 1, it's the log of 1. 0, right? So at that point, pH equals the pKa. So when we're looking at, if you want to make a buffer that has a particular pH, you just search for acids that have a pKa very close to the desired pH that you want to have. Okay? So, and that could be really important in certain situations. That we'll get to a little bit later. All right, so in the third part here, go to our next question. They want us to actually, all right, we'll use acetic acid, right? HC2H3O2, and sodium acetate, NaC2H3O2, buffer solution. So they want to know what the ratio of acid to conjugate base is that you need to maintain the pH at 5. Okay, so they're telling us what the pH, the desired pH of the solution needs to be. Okay, and explain how we would make the solution with the Ka of acetic acid as a Ka of 1.8 times 10 to the minus 5. So we're going to use our Henderson-Hasselbalch equation to figure out what the ratio needs to be. Okay, because we can plug that guy in and take a look at, right, C2H3O2 minus the ratio of these guys to one another. So 5 is equal to minus the log 1.8 times 10 to the minus 5 plus the log of our acetate ion to acetic acid. All right, so minus log. So I get 0.255 is equal to the log of our acetate ion to our acetic acid. All right, so how do I go from log? How do I get rid of the log? What do I have to do? All base 10. So yeah, we just raise both sides 10. So we're going to go 10 to the 0.255, and I get 1.8 is equal to the C2H3. Whoop, I messed up. And that gives us the ratio of the base to the acid, right? But what are they asking for? Oh, with the sodium, do we care about the sodium? It's spectator ion. Like the part that's important is the conjugate part, right? Is the acetate ion, right? Because that's the part of acetic acid. So, well, we just solved it for the ratio of our base to our acid, and they're asking it for, well, what's the ratio of the acid to the conjugate base? So what do we need to do? Let's take the inverse of that, right? So 1 divided by 1.8 gives you 0.55, what they were looking for. Okay, but ultimately, right, what we need to ensure is that if they want this at pH 5, in terms of explaining how we would make a solution, right, we have to have 1.8 times as much sodium acetate compared to the acetate ion. Okay, I'm sorry, of acetic acid. So, and we could do that. All right, we'll finish up buffers tomorrow. Buffers are fun. More ice table. Peace out.